Welcome, everyone. Welcome to the third real lecture of Elements of Machine Learning, in which we're going to be diving a little bit deeper into linear regression, or super simple methods that we will see with a little bit of steroids actually is useful for almost anything and everything. Let's get started. In the first half of the lecture, give or take, I want to answer these four questions with you. So, given that we have a bunch of predictors, is at least one of them useful? Is it worth knowing, or is it all just make-believe, and should we tell our domain experts, sorry, no can do, you need to get better data? If there is at least one that is useful, we have another problem, namely, which ones are those, right? Which subsets of predictors are the ones that we should know about? Could again be multiple, but we're going to keep it simple. Then third, when we found some predictors that are useful, either using the subset selection or not, how well does our model actually fit the data? Can we say something about that? We're minimizing the RSS, but what else? I mean, how well does it do it? And then a related question, but not the same, how accurately can we predict a certain value? If our model says, okay, it's going to be 0.25, how well can we trust it? Those are the four questions I want to discuss with you at the beginning of this lecture. Starting with the first one. Is at least one predictor useful? Last week, we already dabbled a little bit into the wonderful world of significance testing for coefficients. Is a coefficient, is it close to zero or not? We discussed this, right? Remember? So what we have to do in order to tell if at least one predictor is useful, we need to define a statistical test where our null hypothesis is that all of the coefficients, beta 1 up till beta p, are insignificant. Note that I ignore beta 0 because that's just the intercept, and that's we discussed, it's just a flat line, right? Has nothing to do with the interaction between x and y. The alternate hypothesis is that at least one of the predictors is significant. It's a slightly different setup than we had last time. We were just looking at simple linear regression, where we just had one x, and then, okay, does this x does it get a sufficiently non-zero coefficient? We're going to be using pretty much the same tools that we saw last week. We're going to be using f-statistic, remember those? The total sum of squares minus the residual sum of squares. So how much variance in the response is not explained after regression? Well, and quite obviously, if our null hypothesis is that the predictors do not explain anything, we should pretty much be at the same amount of variance after regression than we had before, right? So the difference should be very low. The f-statistic is defined slightly more complicatedly because we now divide this by p, because, well, each of those predictors can explain something. So we need to normalize it. And then in the denominator, we have again the RSS. How much variance does it explain to begin with? And that we normalize then by what are the parameters that contribute to this explanation. Okay, there we have this normalization defined n minus p minus 1. Let me give you the intuition behind it, right? You can mathematically attribute it different ways. We have n data points. So the residual sum of squares, right, is the error that is left over n data points, right? So if we divide RSS by n, this is the average residual that we have left, right? Okay, now why don't we divide just by n? Well, we're estimating a number of parameters, and this number of parameters basically requires us to have at least so and so many data points. If I give you 0 data points, you can't estimate any parameter. If I ask you to estimate simple linear regression or multiple linear regression with 10 predictors, well, you need to estimate 10 coefficients. Actually 11, because there's also the intercept. Well, p is those 10 minus 1, that is the intercept. So it's simply the number of parameters. We need to have at least so many data points in order to even get to an estimate. And in a way, those cannot contribute to reducing the residual sum of squares. We just need them to be able to get to an estimate at all, no matter how good or bad it is, right? That's why we subtract these things. So it's essentially the the data points beyond the number of coefficients we want to estimate, those can contribute to reducing the error that we make. That's the way we should think about it. Now, if we plug in the assumption that we make, and we still live in linear land, then on expectation, RSS over number of parameters, well, that's just going to be the variance squared. This is standard plugging stuff in. Okay, well, if that is true, and it is, then what would be the case if our null hypothesis is true? We have this, namely, the total sum of squares minus residual sum of squares is still going to be the total sum of squares. It is this thing. Comes down to exactly the same. So if our null hypothesis holds, this expectation should go to variance squared. Okay, that is something we can test for, right? We can just see, is this the case, yes or no? Otherwise, so if we do expect that our residual sum of squares is somehow better, right, lower than the total sum of squares, then actually something has been properly explained, then we get a value that is higher than the variance squared. Okay, that gives us essentially a way to test if something is an apple or an orange. And now the nice thing is that this F statistic, this follows, under certain assumptions, a nice distribution, and that means that the value that we get out of this thing, just like with the T statistic that we saw earlier, right, last week, if the value is above or below a certain threshold, we can say, yeah, we can trust this result, or it could be due to chance. Just to answer a quick question over Zoom. So why is it n minus p minus 1 and not just n minus p? Because we also have to estimate the intercept. So there's not just p coefficients, not just beta 1 times x1 and beta 2 times x2. There's also beta 0, beta 0. And without data points, we can't estimate it. Okay, so the F statistic is going to be 1 if our null hypothesis is true. If there's nothing special happening. I mean, it's reasonably easy to figure this out from the total sum of squares and whatnot. On the advertising data that we saw last week, right? So newspaper and so on and so forth, we get a value of 570. Okay, that's pretty extreme, right? I mean, that even without looking at the distribution, we can say, okay, that is probably significant. But in many cases, it's going to be much closer to 1. Is it good enough, yes or no? The F statistics follows an F distribution, just like a T statistic follows a T distribution, and so on and so forth. And it's parameterized by, well, what do we have? We have n and we have p. Right? Those are the three parameters that we have in the definition. So we're on the right-hand side. I plotted a few different shapes that the F distribution takes. And as you can see, I mean, if we have only one data point and p is 2, well, then basically it almost immediately goes to 0, the probability. So you almost always will have an F statistic of 0. And the higher n becomes. So, okay, there's doesn't. What is the trend that we see? Because I don't just increase n. Actually, I should actually here. So we go to n to 10, so we can keep p at 2. You can see that it drops, and we move probability mass a bit away from the origin axis, right? So ignore the gray one. You see that this peak basically gets spread out over a bump here and then. The more data points we have, well, there's also more chances of reducing your error. So this peak needs to be moved further away from the origin. This is essentially what it does, right? So the higher n, the more it pushes it to the right. The expected value goes up, but it still follows this not quite Gaussian shape. But the higher n, the higher p, the more Gaussian it will be. Good. Okay. Now we know, is at least one predictor significant? Is it useful, right? So we don't have to test, like last week, each and every one individually. That gives a number of benefits. So most of you should, actually no, all of you should have taken some class in statistics prior. Otherwise, I mean, this is a bit more of a rough ride than you would have bargained for. Why is it better to test this in one go, like here, rather than testing for axis 1 independently of axis 2, independently of axis 3, and so on and so forth? Because in both cases, we still get the answer, is at least one useful, right? What could possibly go wrong if we test each individually? You here in the front. Exactly. Multiple hypothesis testing, right? That's, just to repeat the concept. We don't really discuss it in the course sufficiently enough. We don't have the time, but indeed, you're absolutely right. What's your name? Jawad? Okay, that's the first time I hear them. That's a very nice name. Thank you, Jawad. Indeed, so if we test many times, then just by random chance, it might be that a test says, yeah, that actually looks significant. Remember, a p-value is, what is the probability that a result this extreme or more extreme was generated by a random, so a non-significant null hypothesis. It could always happen by chance. If we set a threshold of 0.05 at 5%, it means if we only test one thing, we accept a risk that in 1 in 20 cases, 5%, that if the test says yes, it actually was just spurious. If we test twice, thrice, 100 times, this value goes very quickly to 100%. And we are absolutely certain that one of the results that was positive was not. And yeah, okay, which one wasn't? Hence, this is more useful than testing things independently. And yes, you recall correctly, there's also multiple hypothesis correction that you can do, right? But then we're in more advanced statistics land that I want to shield you from in this course a little bit. This is a nice lead up to what we're going to be doing next. So now we know that one predictor is useful. It is more useful. What is the subset of predictors that is useful, right? How can we get rid of all the individuals that are not, such that we have that group that gives us the best worth for our money? Well, we can again do this through a significance test. We can grab some set of predictors, and we can see now if we add an additional predictor, one or multiple, but let's keep it simple, right? Does this add significant information, so to speak? If we would add it, does life get better, yes or no? Okay, what does this mean? The null hypothesis then says that those predictors that we already chose beforehand, well, those are the shiznit, and those should stay, right? Those have non-zero coefficients because we believe in them. And on the other hand, we say all the others, well, no, they're useless, right? The expectation is that their coefficients will be zero. They don't contribute anything. That's our null hypothesis. That's what I have here. And it always confuses me every time I see this again, this p minus q plus 1, and then I stare a long time at it, and then it starts to make sense. And a year later, I see it again, and it doesn't make sense. So if you have questions, please don't ask. No, that's not true. That's not true, but it is correct. It's correct. It's basically we order, on the one hand, the predictors we find interesting, and on the other hand, we have those that we don't find interesting. Right? And then at the last Q of the batch, we say, okay, those are uninformative. We can again use the F statistic because we're going to test over groups. We can do this in one big go in this particular case. We have a slightly different statistic here because recall last time we had here the TSS, right, rather than the RSS 0. Okay, what is the RSS 0? Well, this is basically the equivalent of what we previously had as TSS. Previously, we basically said nothing was relevant. The set of variables against we were testing was empty. And then, well, what is the residual error? That's the TSS, that's everything, right? Right now we say, no, this first set of predictors, those are relevant. So what we now need to do, we need to see how much more variance gets explained away beyond what the RSS is that this first batch already gives us. And this in the book they call RSS 0. Personally would have given the two sets different names, but RSS 0 is the RSS that you get from your set of variables that you somehow already chose to be useful, informative, or whatnot. And then the RSS, that is the regular one, that is overall. And then we can see, okay, is there now the difference between the two? Is this significant? And we can again look at the F statistic. Works exactly the same. In the book, they, for, to me, not entirely clear reasons, they choose to show not the F statistic directly, but they show the T statistic in the form of, well, it's basically the square root of the F statistic. They are joined at the hip. Didactically, if I would write this book, this is one of the few changes I would make. So bear with me, right? It shows slightly different values than you would get straight out of this formula. So we have these values here. This is what we're interested in. And what we're doing here, what they're showing is what is now the additional value of the t-statistic. Additional in the sense that if we take, well, for example, for this one, let's say, so the intercept is not so interesting. We always want an intercept. So this one example is the contribution of TV versus the model that already includes radio and newspaper, and so on and so forth. We could also have done it slightly more intelligent or more exhaustively. If we would have had more variables, then you could have had these two versus these three and so on and so forth. But it's a simple example. And as you can see, TV gets a very high t-statistic, and recall this is the square root of the s-statistic, so this is big, right? TV is significant. Same thing for radio. However, newspaper gets a very small value here. And essentially what this means, small, right? Ignore the negative, I mean that don't break your head over it. Small means not significant. Newspaper does not add anything if we are already investing on TV and radio. It's just a spillover effect, right? We already established this last week at the end of the lecture, right? That it really looked like this, but here we have it again. Good. Now, this was great. This was good stuff. Yes. Good question. So this is exactly what I meant that didactically. So this book, I love it in many, many ways. All Platonic, of course. I would have just given you the f-statistic here because that doesn't become negative. Here, because the coefficient is negative, then so interpret this t-statistic as the square root of the f-statistic. And that it, hence ignore, please, the negative, or stay in imaginary land. That's also fine with me, right? So, like I said, this is one of the things that stupid book. Yes. It's in the end the same thing. We're still testing whether the coefficients are close to zero, yes or no. Last week, we were doing this one by one. And that was effectively what we did through the t-statistic. And the f-statistic is sort of the t-statistic on steroids. Hence, think of it as the t-statistic squared. Why? Well, it doesn't test things individually. I mean, it can do that, but then it reduces to a t-statistic, and this is what's happening here. But it can test entire groups against each other. And that avoids us having to do lots of tests against each other, and therewith the chance that you have a spurious result, we can now test things in one big go. That's the advantage of the f-statistic compared to what we did last week. And this is, besides the t-statistic reporting here and the fact that this example is a bit too small, this could be illustrated a tiny little bit better. And I had good hopes that in the second edition they would do so, but they didn't. And probably there's very good reasons for that that are beyond me. Yes. Yeah, so why would we use these? Exactly, we shouldn't. So point being that t-statistic is good for this individual pairwise, right? It can test essentially one coefficient or the difference of one coefficient. That's exactly what in this example happens. This is why they should show this t-statistic, because you don't need the f-statistic in this example. So long story short, perhaps next year I should show a different example here. I should handcraft it away from the book to avoid all this confusion. The point is that in this particular case, because we're leaving one thingy out, we can use the machinery that we saw last week. The machinery that you see here, we can test not just that we take out newspaper, but we also take out advertising on Twitter, both at the same time. And that is something that last week we couldn't do, because last week we're testing, is this one coefficient zero? If we want to take out newspaper and Twitter, because I don't think you should advertise on Twitter right now, but hey, your mileage may vary. Then you're testing essentially are two coefficients zero, right? And last week we couldn't do that, now we can. But even though now we can, we don't. And that's why it all gets a bit mixed. Right? So is that sufficiently clear? how these two, the stuff that we saw last week and this week, how this now matches. Yes, you in the back. Wouldn't it be exciting? Wouldn't it be exciting to learn just that, right? That can you wait 2 slides? Good. Okay, so first, what could possibly go wrong? that we first need to go, right? Suppose that we don't just have TV, radio, newspaper, Twitter, and what else, but we have many. We have many, right? I mean, well, there are, of course, infinitely many advertising channels. My favorite example is still to go to bioinformatics, and we have many genes that we somehow sampled activity over, right, or proteins or whatnot, right? But many predictors. One thing that we're interested in, let's say the severity of a disease or something like that. Suppose we have 100 predictors. Well, in principle, we can just do exactly that, right? And that's just like F statistic allows for it. However, things start to become a little bit murky. Suppose that we have 100, and we have the setting where we have 100 predictors, and we now, and we have this data, we now generate a random response. There is no relationship between the gene activations that we got, right? I mean, that they got in the lab, or think of your favorite type of data, and the response. It's completely random. This is a sanity check. Should we find that any subset of predictors is significant towards this random output? No. There's no relationship. I generated the output completely randomly, independent of the rest of the data. Well, so then probably, right, everything was statistics. Statistics is sound, should be all right. Yes, maybe not. We're actually almost guaranteed to find a significant result. Exactly what Joel just said. It's not Joel. Joel, okay, Joel. Okay, then I misunderstood your pronunciation. Joel, I know the name, and it's still a nice name. Yeah, it would be a bit unfair. It's like, Joel. Okay, that's boring, right? No. No, we're practically guaranteed to find a significant result, just because, I just already preliminarily explained, if we do a statistical test with a particular alpha, an acceptance of a certain risk, so they set the threshold at 0.05 or 0.01, if we just often enough different hypotheses at the same threshold, by chance, if we test with an alpha of 0.001, 0.1% the probability of doing something, of accepting a wrong result, and we do 1,000 tests, on expectation there will be at least one spurious result. If we test 10,000 things, 10. If we test 100,000, 100, and so on and so forth. So we need to be careful not to test too many things, or we need more advanced statistics. Well, this is what also goes wrong here. The T statistic and its close cousin, F statistic, do not adjust for, well, let's say the number of tests that they're doing under the hood. They do not adjust for the number of predictors. And F statistic does, because we do this in one big go, but still you're doing, so one big test. If we're now going to use the F statistic for many different subsets, then again, we're doing many tests, and we fall exactly into the same problem. Now, especially, this is another thing. I mean, so if we have more predictors than we have data points, well, then we're really then there's really some trouble. Because effectively, we're going to have to estimate more coefficients than we have data points for. So just going back to the formula of the F statistic, this thing here, well, we can still compute it, but it starts to become nonsense, right? Or nonsense. I mean, you can still interpret it. It still has a proper interpretation, but it's make-believe. The system is underspecified, as we say. How to deal with that? I mean, can we still do some kind of regression, right? Or is abandon all hope he who enters? Yeah, chapter 6, we regain some hope. There is a way to still get reasonable results. Unique results, but still, the moment that we have more predictors than we have data points, you need to be very careful. We're treading on very thin ice. Okay. To answer your question, what was your name? Okay. Perhaps if you type it over Zoom that I can, but on this distance, I'm sorry. That's perhaps in the break you can tell me. I mean, as you notice, I like to learn a few of your names because it makes the interaction a bit more fun on my side. So Boranje, was that? Joy. Okay, Joy. Okay, good. Then the exact pronunciation I'll get later. Joy. How do we now find these subsets? Because previously I was saying, let's assume that some part we believe is good, and now is the rest then bad? Okay, how do we find these subsets? Well, what we yeah, so it's not just on one, but on, because if it's just one, then we could, in theory, just do t-statistic testing, right? I mean, that's all fine. We've seen how this works. We need to correct for multiple hypotheses, but okay. But which set is it now? Chapter 6 is again the real answer, but we're not there yet. And I do feel the need that we answer this question, not just because of your question, but in general. If I would have chosen not to answer this question, so okay, I'm just turn off the screen for now. I mean, figure it out yourself, right? And we speak again about this in 15 minutes. You probably would have come up with one of the solutions, and I'm going to present just in the next few minutes, because the basic things work very often. And if you did not come up with any of those ideas, then okay, sorry, then better luck next time. What we could do is very simple best subset selection. We just simply try all subsets of variables. So the empty subset, is there anything? Okay, well, that basically we already included. Is there any coefficient that is significant, right? That was the test that we started with. But we could do just TV, just radio, just newspaper, just TV and radio, TV, newspaper, and so on and so forth, all subsets. Okay, well, we can do this, right? And if we don't have very many predictors, this works. Why not very many? How many subsets are there? 2 to the power p. Grows exponentially, right? And if you want to scare a computer scientist, you whisper exponential in their ear, right? That's so. If we have 30 predictors, 2 to the power 30 is already a lot. 1 trillion. Or depending, actually, billion, trillion, depending on which side of the big pond you're from. Okay, now, you could say, okay, that is problematic because that just takes too much time and you would not be wrong, right? But I strongly believe when we're trying to approach something scientifically from a research angle to accept black hole computing as a reality. What is black hole computing? Well, you know that in a black hole, everything gets compacted, right? I mean, including time, things go very quickly in there, right? So that's the theory of relativity. So what we do, we just write a very inefficient program that just goes over all these things. We throw the computer that runs this into the black hole. It starts to run really fast. The only problem that we need to solve, and we is now the physicists, how do we get the information out of the black hole? I've been told that this is difficult, but hey, I'm very hopeful. Black hole computing is a very useful theoretical construct to see what could we do? What would be the best solution if we're lazy when it comes to efficient programming or understanding problems? In this particular case, that would not even help, sadly. Because how do we now evaluate these subsets? Besides significance, what we're going to get is that essentially, the more flexible the model is, the lower the error is going to be. Bias and variance. More features, more flexibility. Sure, we can squeeze out more and more and more. It's just going to happen. So the training error is completely useless by itself. Also, note that just in significance testing, we'll get there in a sec. If you now have to, if you run this many tests, and you have you accept the risk of 1% or 1/10% of false discovery in practice, then, well, perhaps you know the concept of Bonferroni correction, multiple hypothesis testing. Essentially what you do is you adjust the alpha that you are willing to take, this 0.001, you divide it by the number of tests you're going to run. Which now means that all of a sudden we have an alpha of, well, 0.0000000001. What does that mean? That means that we will only accept coefficients that are ridiculously significant. We have a very low, what we call statistical power. So if there is something that is ridiculously significant, we will find it, but there will be plenty of solutions which we're now throwing out. Well, we're throwing the baby out with the bathwater. Is that what you say in English? At least what we say in Dutch. Het kind met het badwater wegwerpen, maar goed. So one for only correction is also not going to save us here. But even if we just look, if we ignore the significance, this is going to go down. So what we actually need, we would need to evaluate the test error. We don't know yet how to do this, right? That would be the right way to do it, of course. We're going to learn this in 2 lectures from now. 3. Let's continue with this subset selection, this feature selection. Because just enumerating all these subsets, there's way too many. Well, let the physicists figure out black hole computing. For now, we need something a bit more practical. What would be the first algorithm that you would come up with? Forward selection, probably. We start with a null model that doesn't get any predictors. We now find that addition to this model that gives us the best gain. Right? Okay, so we fit P models, right? Each with just one predictor. We check the one with the lowest RSS, and well, we keep on doing so, right? We have the whole sequence of models. And we continue until some stopping criterion is fulfilled. Maybe some significance threshold. Maybe you say, okay, well, I want the RSS needs to drop at least so much, or whatever. We will learn a number of the stopping criteria, right? This is why I keep it vague. If we can do forward selection, we can also do backward selection. What is backward selection? We start with the full model. Okay, now we need to get rid of stuff. Okay, well, one way how to do this, take each predictor individually out temporarily, see what reduces the score least, right? So what basically increases the error least. Or we could figure out which variable has the highest p-value, which one is the worst variable of the batch. 2 completely viable approaches, right? We kick that one out and we keep on doing so until, well, again, stopping criteria hits. Well, if we have forward and we have backward, why not do both? Yes, this is called mixed selection or smart selection. We start with an empty model, we grow it like in forward selection. Basically, the stopping criterion becomes the significance. You already have all the machinery in the previous slides. And now at the end, well, it may be that along the way, we picked up a few features that looked good when we were considering them. So we picked up a feature A, let's say X17, and let's call it A for now. And a bit later, we also picked up B and C. They were still significant, but with B and C, we can actually explain away A. We don't need A anymore. Now, in forward selection, we would be screwed. A is never going to leave. In backward selection, well, we don't have this problem. In mixed selection, we also don't have this problem because we first grow and then we shrink. And then depending on how many CPU cycles you want to waste, you can grow again and shrink again until, well, you can't find anything. Typically, one growth, one shrink phase is fine. These 3 algorithms, not just for subset selection, I'll be with you in a second, but also for plenty of other model selection problems, combinatorial search problems in general. You have growth, so bottom-up search, top-down search, and this growth and shrink, especially in causal discovery. The equivalent of that algorithm, that still is king. There are highly engineered algorithms that are slightly better and whatnot, but that is basically everybody's nightmare because it's so simple and it already does so well. It's very difficult to beat it. You had a question, sir? No. No. So question is, so you mean like the forward and backward equivalent or the different variants within backward? Okay, so let me re-explain. And I also can, in a way, reiterate the question in the explanation. So basically the question is, which of these options are equivalent? Are they just different rewordings of the same thing? That's roughly what it comes down to, right? Now, on the one hand, forward selection, start with empty, add that feature that, well, improves your score most, right? That is one strategy until some stopping criterion hits, right? That could be significance, that we stop adding things become the moment that the best improvement is insignificant according to your F statistic, T statistic, whatever you choose, right? That is one option. You agree with me? Yes. Yeah, so I'm going there. I mean, bear with me. So I was just reiterating it was the forward search, right? So which one improves the most And if this improvement becomes too small, stop. We could also add in every step that coefficient that has the highest significance. Significance and RSS, they are related, but they're not the same value. So already in this forward search, we might, in the let's say the second or second iteration, we choose x3 if we optimize directly RSS, but if we optimize significance, you would choose x6 or x7. So does it constitute the same model? No, not necessarily. It could be, but not necessarily. In backward search, that was what your question was about, right? So if we now put it in reverse, we start with the entire thing and we throw stuff out, same answer. We can either throw that thing out that contributes least to the improvement, right? So if we take it out, our performance drops least, or we can try to find that coefficient that has the highest p-value that is least significant or is insignificant, right? And this will often coincide, but not always. So hence you can do both. Yeah, does this answer your question? Good. Okay, and on Zoom. So, yes, okay, the first question. Yeah, so I'm trying to repeat the questions in my answers, not not just that the people Zoom know. Second, Alexander. Where's the point that we decide that the improvement is insignificant? Well, we set this significance threshold, alpha, 0.05, 0.001. And if the p-value is higher than this threshold, then it's insignificant, right? And it constitutes a risk that we're not willing to take. So, out. Good. Any further questions on subset selection? Yes, you. So the question is that whether for these three methods, the order in which we add features into our model, into our current subset, if this matters, yes or no. And the answer is indeed, you gave it yourself, yes, this matters a lot. If I choose x3 first, rather than x4, well, that may just mean that I do not choose the other one. Suppose that x3 and x4 are just copies of one another, or with a little bit of noise. The one test may choose this, the other one I choose that, and I will not choose the other one, which we will get to this problem, or the problems that this creates, a bit later, right? That features may look too similar to one another. What happens then? Collinearity, we call this. Any further questions at this moment? No? Good. And we go to, this is now the third or the fourth question already. I lost count in all the excitement. The third one. How well does my model fit the data? Well, we have RSS, right? And we have root mean squared error. Lower is better. Last week I also discussed a few other scores. R squared is one of them. R squared worked very nicely for the univariate case for simple linear regression. How does it now relate to multiple linear regression, where we have many predictors? How does this work? Well, what we have is that for the univariate case, the R squared is essentially just a correlation, Pearson correlation coefficient, we discussed this last week, between x and predicted y squared. For multivariate, yeah, we would have many, many x's, and Pearson only allows one, so that doesn't work. However, what does work is just replacing x with y. So it's the correlation between the actual outputs and the predicted outputs. And of course, if this is a straight line, yeah, well, then we did a very good job. Then we can be proud of ourselves. Right? This is how you can interpret the R squared. Now, if we don't want to do this significance testing all the time, right, and we could optimize RSS in the subset selection, but we could also optimize R squared, because why not, right? I mean, it's one of the scores. Why should you always be careful by just optimizing a score and not taking significance into account? You have an example. If I don't have the empty model, but I have the model with just TV. The R squared, that model is 0.612. Not bad, could be better. I add radio. Ooh, look at that. 0.897. Okay, that's a pretty high jump, right? However, the full model, it still wins. The difference is, of course, minute, right? It's really behind the comma, so I didn't even want to add it. But so you already feel like, okay, no, we should not be doing this. But if we directly optimize R², that's where we land. The full model, every predictor included, is always going to get the best R², no matter what. So we don't want that. We don't want that, right? R² monotonically increases, if you want to put it mathematically. So whenever we add variables, no matter how weakly they are linked. We will see some examples of what happens with that a bit later. So just measuring R² or RSS, or even the significances over coefficients, we need to be very careful. We really should be considering the test error. But like I said, we're not going to do this until a little bit from now. What I can give you as a tip and advice to always do, I know I've said this already in the first lecture, but I need to repeat this because you always need to do this. Always inspect your data. Always inspect the residuals. Always look at this stuff, analyze it. Don't believe that, oh, I got an RMSE or an RSS of 0.42. Yay, great. What does it mean? This is an average. Never trust an average. There's always outliers, right? Does it have a big plume? Is it a small plume? Is it, as you can see here, I mean, is this flat plane, is this a good fit to this data? Just by looking at it. No, this data is not flat. It's not linear. The data is banana shaped in space. We need not a flat plane, we need a banana. Okay, well, if you don't look at the data, then you wouldn't see it. And well, okay, you have a pretty decent RSS, right? I mean, everything is fine, but yeah, bias and variance. We would have a lot of error in the bias part because we're using the wrong model class. We're trying to reduce as much of the variance as we can, but right. So keep this always in mind. Always inspect your data. And I know, not because you're lazy, but no matter how often I say this, you're still not going to do this often enough. And why do I know this? Because, well, even my own PhD students who hear this regularly don't always do this. Domain experts that I talk to who make their money by analyzing data, they forget to do this. They don't look for bananas in space, and they should, right? So please think of bananas in space. Okay, technically it's 5, so normally I would introduce the break right now. I want to continue for a minute or two further because I want to answer the 4th question, and then we take a break. How accurately can we predict? Not just how good is the model in general, but how accurately can we predict one specific case? In a way, a much more important quantity. No. Okay. Not sure what happened with the animation here, but okay. Suppose that we predict one particular. We get an output. We can output an estimate, right? I mean, that's of course how good our estimates of the coefficients are will, well, determine how good our output is going to be if the model class was correct and all that, right? Now, that allows us to compute confidence intervals, not just for the coefficients, which gives us a way like how good is my model, but as we'll see, also intervals for predictions. What is the interval in which we expect that if we predict it's a this value, how wide is the interval of where the true value is expected to be? Yeah. Bias and variance, bananas in shape, in space. What is now the definition? So confidence interval, you've already seen it, right? So we have now some average plus minus a t distribution. Oh, let me also animate this in. Root mean squared error. And well, we have a Gaussian assumption here in the end. This is these two tails that we saw already last time, right? Where we choose by alpha, and last time I said, okay, we choose then the 2 sigma, right? So alpha was set to 2 essentially. That's not true. We set sigma to 2 sigma. Any value beyond significant, anything within, that is, well, so significantly different within is where we expect it, right? 95% confidence interval. Now we can do exactly the same, like here, for the prediction interval. What is now different? Well, Look very similar except for this part, 1 over n. Because we're now not averaging out all the errors that we could make in estimating the coefficient over all the data points we have. No, we now are really being put on the spot to make one prediction. This is 1 out of n. It adds an additional risk. That's what this 1 over n comes in for. What does that mean? That means that a prediction interval, if we choose the sigma again, such that it's a 95% confidence prediction interval, that is that interval that we're 95% confident that the true value is. This is always going to be wider than a 95% confidence interval for a coefficient estimate. Because this is averaged out. We had not so much guesses, but we have a lot of data. Whereas for this one prediction, we have only one shot, right? Mom spaghetti and all that. So just to give you some examples, I mean, the formulas you can just fill in. This is not so exciting. I mean, if we say that we invested 100,000 in fee, 20,000 in radio, what are then the confidence intervals for sale, right? Under the model that we learn. Well, the confidence interval for the coefficient is relatively tight, well, it's not so bad. The 95% prediction interval, quite wide. So what we're predicting is the value in the middle, but Okay. May not be exactly what you want, such a wide interval. And of course, with more data, better estimates, I mean, the confidence interval, the prediction interval will shrink. But you have to always acknowledge that a prediction interval will not be as tight as you want it to be. There is always a risk that you get things wrong, right? Something that you really need to be aware of. Prediction intervals, wider than confidence intervals. How to compute them, almost the same, except that, well, 1 over n. Right? Good. Time for a break. So we took now a little bit longer to answer the 4 questions that we decided, that we focused on. We took a little bit longer to answer these 4 questions, but I think there was a very good discussion, so I enjoyed it. I think this was definitely worth our time. You may remember that at the end of last week's lecture, I told you that what we're going to be talking today about was how linear regression, how the stuff that you learned last week, how this is already kind of a superpower, right? How this very simple model that is ridiculously unrealistic drives so many parts of machine learning, so many advanced models. Well, so far we haven't really gotten there, right? We have seen how can we now select features, huh? So there's lots of useful things, but how powerful is it now? Because it's still so limited, right? Can't we upgrade it a little bit? For that, I need a slightly different data set. I need a credit data set where we have 400 data points, and we don't just have quantitative predictors like we had previously, so how much did we invest and whatnot, right? But we also have a number of qualitative predictors, where it's really like, well, apple, banana, orange. There's no number, right? In this particular case, you have gender, male, female, studentship, yes, no, status, married, no, married. But you can also have, of course, features with multiple values. In this case, we have regions. They choose 3, north, south, east, somehow, or west. I don't know. One of the 4 has been excluded. They're a bit regionist in the book. How can we include those? Can we include those? Actually, yes, almost effortless. Especially the binary ones, super easy. We just create a dummy variable, for example, the value xi, so for some random variable capital X, which we just give the number I, right? I mean, it's basically p plus 1 or whatever. And this takes the value 1 if the person is female, and it takes the value 0 if it's male, or the other way around, whatever floats your boat, right? Yeah. We're very inclusive here. If we do that, what we get is a model that looks like this. So ignoring all other variables, right? We're keeping it simple. So the prediction is going to be the beta naught. So we again have an intercept. We're going to have a coefficient beta 1 times the value of xi plus some error. That's the model that we assume. And effectively, what we have, if we want to make a prediction, that if xi takes the value 0, so in this example, if they're male, then, well, x0 is 0, so this entire thing drops out anyway. So beta 1 for the males, well, we don't have. For the females, we do include beta 1. That's essentially what the model reduces to. Okay, easy peasy, right? Binary features bumped just like that. So how can we now interpret this? Beta 0 is the average credit balance for males. Beta 0 plus beta 1, that of the women. There we are. That's how you can interpret linear regression with a qualitative binary attribute. Yes? No, next week. So the question was, okay, so hey, but now X is binary. What if Y is binary? Well, then we're not talking about regression. Then we're talking about classification. And that's what we're going to do next week. And the week after. So yeah, that's... No, here we're doing still regression, but now one of the predictors is binary. Alternatively, rather than 0 and 1, right? Because 0, that sounds perhaps a bit judgmental. Why don't we just make it 1 and minus 1? Not sure if this is less judgmental, but okay. Does this work? Sure. We can definitely encode it like that, right? Can we then also encode it like 100 and minus 500? Yeah, sure, whatever. But I don't recommend it because the interpretation starts to become a little bit more difficult. With 1 and minus 1, what do we have? Well, we get a model like this. If the ith person is female, then we have beta 0 plus beta 1 plus whatever noise. And for male, we have beta 0 minus beta 1. Hey, so the plus and minus 1, they actually have a use because it's a deviation from an average. Beta 0 now is the average over everybody, and then we have the deviation from the two. So how you encode these binary values, that affects how you should interpret your model, right? The coefficients that you get. It does not affect at all the quality of the model. So how good it can possibly fit your data, right? But not at all. But what you can do with it, yes. So interpretation. So from the inference side, yes, there's a difference. Prediction side, not at all. What we see on the data is that gender is completely insignificant. A p-value of 0.669. So okay, that's reassuring, right? Gender should not affect, of course, at all whether somebody gets a loan or not. What if we now want to include a predictor that is not binary, but there's multiple values? Here we have the truncated wind directions. We have south, west, and east. So I don't know what happened to the north. I mean, I feel I'm in this picture and I don't like it, or I'm not in this picture and I don't like it. What is it? What do we do? Well, we just use multiple dummy variables. We can use an xi1. Numbering is a bit. If somebody's from the south, yes or no. Same thing from the west, yes or no. And the third one we don't need, because we know that somebody has to be from somewhere. Right? There's only 3 possibilities. If they're not from north or from the south and the west, then they're from the east, because the north doesn't exist. We get this model, and we can again interpret the parameters like contributions to an average. We could also do it slightly differently. Oh, actually, no, wait. Essentially what we have is beta 0. That's the balance for east, or the one that we didn't encode. That's the baseline. And then south and west, those we have coefficients for. Those are the deviations for the other two. So, still works. Testing significance. Well, in the previous case, with the binary variable, it was easy, right? We could just interpret it as just your plain, stupid, normal regression variable, right? A plain predictor, no problem. Now we have 2 predictors that together encode one thing, right? So we cannot use the standard t statistic. We need to use the f statistic. We need to test this group together. You can't just test, is it just south or just west, because they're joined. In this case, also where you're from, no, which is also good, right? I guess. Not I guess, it's just good. Okay, so now we already know how to include discrete variables. Let's actually go back one step. You can already see that things start to blow up a little bit if we have many categorical values, right? So if it's red, blue, and green, still fine. If we go to 16 point so many million different colors, right? starts to become a bit more tricky, right? That you can do it, but then you get a shit ton of parameters. So you need also a shit ton of data, and no. Yeah, so it's a bit of a hack, this, but hey, linear regression does allow for it. So we can at least make it work to a certain extent. Now, one other thing that may have already crossed your mind is that in linear regression, we just have a stupid additive model. It is a beta 1 times x1. It's a beta 2 times x2. And all are additive. We never consider that x1 and x2, they may have something to do with one another. And there's no way for us to control for this, to correct this, right? We treat every variable completely independently. So in our example, TV advertisements, radio advertisements, and newspaper advertisements, they have something to do with one another. Right? The one may boost the other. We already established nobody reads newspapers, so we shouldn't advertise there, but people who well, listen or watch TV also listen or watch radio. So there is some interaction. Treating this completely independently is stupid. How can we combine? Well, what would be the simplest way to do this? Let's introduce a new variable, which we just gave the name xp plus 1. And what is the definition of xp plus 1? That is a function over 2 or more predictors we already have. Well, what function could we have? Let's take the product. Product is a good function, right? For example, x1 times x2. Well, that is a new predictor. And we can also take x1 times x3, and so on and so forth. We could also, it goes far beyond this slide, intentionally, but x1 squared. It's also good that x1 times x1, right? x1 cubed, x1 times x1, sure. A logarithm of x1, or go wild, right? I mean, whatever floats your boat. I mean, just we can add tons of new predictors, pseudo predictors, or functions over predictors that, well, as long as they somehow make sense for you and I, they allow us to fit the data better. Okay. We'll revisit this topic a bit later in the course again, but linear regression, there we're just using just one x, one coefficient, but these x's don't have to be literally the columns in the data. They can also be, well, columns that we generate ourselves from the columns in the data, like squares, interactions, and whatnot. Back to interactions. TV and radio, we have a suspicion that they interact. Why do we have a suspicion that they interact? There's a banana in space. That's why they interact. If they would not interact, it would be flat. But no, we have a banana. Okay. Banana means that, hey, there's some curvature, right? There's some quadratic-ish relationship, but not just quadratic in one, and it's in the relationship between the two. So that means we need to include a factor x1 times x2. This is what we do here. And this is essentially a column in the data that we just generated from the data we already had. Everything is fine. We can just throw linear regression at it. Previously, we had p predictors. Now we have p plus 1 predictors. Nothing changed. Linear regression just eats it up and spits out a model, right? And what's best of all, if the interaction x1, x2, if this is significant, if this really adds something, well, how could we possibly determine this? Do we have any tools to determine this? Yes? For example, yeah, F-statistic. Yes, exactly. Or even individually, if you just want to test the interaction without the rest, and t-statistic, it's just a random variable. There's nothing special about it. So all of a sudden, we went from simple linear regression last week to multiple linear regression, right? Still fairly straightforward. Right now, well, it is still linear regression, but, well, is it still linear? Not really, right? Not really, in a way, yes, right? Is it still additive? Yes, but also no. It depends a little bit on how creative are we in creating these functions over the features we have. These functions, I'm already preempting a little bit one of the future lectures. So here you can essentially see that we have now this x1, x2 is essentially, let's say, an x3, which is defined as a function over x1, x2. These functions we call basis functions. We have some input data, x1 up to xp, and then we have a set of basis functions, which are just functions over sets or individual predictors, and they spit out, well, let's say a generated table. That's how you can think about it. And this generated table, we throw to linear regression, and there we are. Which set of basis functions to use and which ones have which advantages, disadvantages, we'll discuss later. Good. Okay, so yeah, well, there we have it. I mean, we can interpret it. This is all fine. But, why is there a tilde? Okay, this tilde here is nonsense. Yeah, in the example, okay, let's now see. Already said. We can use T statistic, F statistic. Up, look, TV times radio gets a very high significance value. It really adds something, right? There was truly a banana in space. So, strong evidence, very good. Now, essentially what we were doing, we now allowed our model interactions. Right? This is what these functions over multiple predictors are. How does this work if we have a regression variable, so a continuous valued one, and a discrete one? So studentship, right? Or gender or whatnot, right? The ones that we already seen. What does this now mean? Now we need to be a little bit careful. We need to be a little bit careful. We need to think on how to massage it into linear regression such that it does make sense. So for example, here we now have, we want to predict the balance on somebody's credit card or whatnot, right? And we regress this as income on the one hand, that's the one variable, and the other one, is somebody a student, yes or no? Most students typically make less money than somebody who's not a student, right? Unless they're not a student yet, but those people we ignore here, right? So there is going to be some offset. Well, if we regress, we're going to see this, which, yes, students in general are a bit more poor. Wait a second, is this the balance? I think this is the drawing. So basically how much debt people have, not balance. So it's more the negative balance in a way, because otherwise it doesn't make sense. We have very rich students. maybe, right? I don't know. The book is written by people from the Bay Area around San Francisco, Stanford and whatnot. So not necessarily the poorest, I don't know, but probably it's just read it as the how much debt do they have. And the income is in thousands of euros or thousands of dollars. So I'm yet to meet a student who's making 150K a year, right? That's good on you. But I doubt that there's just going to be that difference, and that's that. That doesn't feel right. You can, as a student, have a reasonably well-paying job, but with a ton of experience, you're going to get a lot more. This is not incorporated at all. What we need is an interaction model that allows for interaction with studentship and your income. So how do we do this? Well, just like we basically saw already, we now have a model where we have basic income. And what we now say, well, we have studentship. This is basically the offset that we already had previously, right? 0 or 1 is somebody student, yes or no. And then beta 3, studentship times income. And if somebody is not a student, then beta 2 disappears because they're not a student. And well, if they're not a student, beta 3 also disappears because 0 times income is also 0, right? So we have a new model. Right now, that we do allow for interaction. And what we see is that the balance does behave more sensibly. It's not just a simple offset. Is this now significant? How would we test this? You already know the answer. Let's move away from this example. Don't like it anyway. I was already hinting at that, where you can also add in other functions, other basis functions, right? I already said that we could square x1, and we take it the cube. All of a sudden, we're in the land what we call polynomial regression. We can consider polynomials up to nth degree, or nth, we're already using n, kth degree. Right? So basically, for every predictor we have, we take it both to the power 1, okay, just itself, to the power 2, all the way up to power k, right? And we do this for every predictor. So we're blowing up our predictor space by factor k. Very often, this is very useful. In my experience, most real-world datasets, they have a strong linear component, which means if you just apply stupid linear regression, you're already going to get quite a lot of variance you can explain. But there's always something a little bit more fine-grained. And polynomial regression, even without interactions, can lead you there very, very often. Here we have an example where the mileage, so how far can you drive your car or whatever vehicle you have on, in this case, a gallon of gas, 4 point something liters of gas. But I didn't want to Europeanify this example, but maybe I should. And maybe I should update it, that it's more like, okay, on how many kilowatts can you drive, how far, right? But, we can set this off against, okay, how powerful is your car? Right? If you have like a small car that doesn't weigh so much, then you don't have like a super powerful engine. And typically you get a lot more mileage out of your car than if you have some racing monster, right? That just been, it's the gas guzzler, as they call it. So we want to include, now in this particular case, horsepower squared. Or maybe, well, in this case, that to the power 42, right? If we have a polynomial to the power 42, sure, why not? We want to figure out what is the right order of the polynomial. We can fit many of them. We can do linear, right? That's polynomial of degree 1. It's just the yellow line here. Degree 2, okay, that's this one. And then green, degree 5. And well, okay, that starts to become perhaps a little bit too squiggly. Maybe we need something in between. We once again need to see what is now the right model. It's not exactly what we test with an F statistic, T statistic, right? Because there we can't, basically we need to offset now the flexibility. And the higher the order of the polynomial, the more flexibility we add to our model, the less bias we have, but the more variance we introduce, versus the other hand, I mean, more restrictive, but yeah, more bias. So what do we get here? Horsepower squared, T statistic is nice and high. So looks good in this particular case, but if we now look at many of them, also look at the R squared for the linear and for the quadratic. Oh, for the quadratic, it's much better. But don't be fooled just immediately, because as we saw, R squared increases monotonically. And unless we explicitly only consider the squared predictor, and not the non-squared, the plain one, but we have two variables, and well, we can explain more. We know that R squared monotonically increases, not decreases. Basically, the degree 5 overfits. Where does it actually, so just as it already play a little bit towards, I think 3, 4, 5 lectures ahead, where would you say, looking at this diagram, does the overfitting or will the overfitting hurt us most? I heard somebody say something. Was it to me? Ah, yes. So let me just move the, I put the cursor here, right? Just say left or right. Your right is my left, so here. Oh, here, okay, so, okay, good. Okay, then it's my right, and your right. Oh, that's correct. Okay, if I don't have a screen, then yeah. Okay, so yes. Okay, here. Why? Because it's correct. What? We don't have data there. Exactly. So we choose here a model that goes sky high, right? So we make this decision on no data at all, right? Remember what I said in the first lecture, machine learning is great at interpolation. It really sucks at extrapolation. When we don't have data, don't trust it, right? Unless you make really strong assumptions about how the world works, etc., etc. This, if you choose a polynomial of a too high a degree, extrapolation is going to be really bad. Interpolation may be good, extrapolation really bad. So we could maybe then specifically say that, you know what, within the domain of roughly 50 up till 200, where we have data, it follows the 5th degree. And then at the end, well, let it not shoot off into space, but maybe we should reduce the flexibility at the ends, right? Because then, based on the data we have, we can sort of see, okay, it goes roughly in that direction, and we don't have data, but it's a bit. That is the idea of natural splines. You will see this in a few lectures from now. You can already nom on the idea. Good. So far on, well, powering linear regression up. So we can do a single variable, simple linear regression. We can do multiple linear regression. We can apply basis functions, which include interaction functions. We can include categorical features. Okay, there's almost nothing left to stop us, right? And that's almost true. It's almost true. So in a way, we could now well, actually, I need part of next week's lecture. And then we can boost directly to deep neural networks. And I can show you, in the end, what they're doing is a really smart way of finding basis functions. And that's all they do. In the end, it's just linear regression. And I would not be wrong by saying that. There are also other interpretations, and those we will see along the way. But as anything, there are pitfalls. It can go wrong, and it will go wrong. And you need to know when is it going wrong and how can I catch that. So problem one, nonlinearity. If we assume linear regression and we haven't used the right basis functions, how can we catch this? Well, we need to look for bananas in space, always. What we have here is a so-called residual plot. I'm not going to explain you how I created this, but I do assume that you are able to do this by yourself. In fact, I want you, also for the assignments and future assignments, to be able to draw this, and do this, practice this. Why? Not just because it's fun and I think that you have nothing better to do. What we have here is that for specifically fitted values, these are the inputs, how wrong does it go? Well, what would we like this figure to look like? What would be the ideal shape? What would we like to see? Flat line, exactly. I mean, actually, if it would be like a perfect line, just at 0, right? That would be good. Okay, that would also mean that somehow there was no noise in the system. There was no irreducible error. Okay, perhaps a flat line is a bit too much to ask for. So if there is some residual noise in the some irreducible noise in the system, what plot would we like to see? You were already close, so. Exactly, yeah, so yeah. Exactly, some confidence interval. What you're doing like this, but I hope that you mean this. Because if it goes like this, then well, it's not a banana in space, but it's still, I mean, it's, it's for the wake of a rocket ship or something like this. No, so we would like this to be basically a Gaussian centered around the 0 line, right? And then, well, lots of points on or around the 0 line, and then, well, fewer and fewer further away. But we don't want a banana. Okay. If you see a U shape like this, or actually any shape different than just this Gaussian band, that means that something is wrong. And the more wild the shape is, well, the more wrong it is, right? So suppose that it looks like a wiggly type of thing. What could we possibly have done wrong? Well, probably there's some sinusoid that we need to model, right? Some periodic function. Here, well, because of the U shape, it indicates to me that perhaps we need to have a quadratic or a cubic function included. Let's do so. Oh, look at that. This was modeling the mileage with just a linear model. We already saw that we should include the squared. If we include the squared, it looks like this. It really looks much better. It's almost the Gaussian strip that you asked for, right? Is it perfect? Not quite. The red line, this is when we fit a spline. You don't know yet what a spline is. Well, I told you what a natural spline, what makes it natural, huh? The restricted ends, but it's a very fancy moving average, but a really cool way to do so. That's what the red line shows. If the red line would really be on the dotted line, then we would be super happy. There's still some structure left, but okay, this we can let go. This we can let go. Second problem. So what can we do? So if it's not linear, right, we can detect this through the residual plots. Learn how to plot a residual plot. 2, correlation of error terms. I already bashed quite hard on many of the assumptions underlying machine learning, right? And that they're ridiculous and they're stupid, but hey, we need to do something. One of those assumptions is that all data was generated completely independently. And it also means that all the errors are generated completely independently because there's no crosstalk between points. This is nonsense. This works if you generate your data yourself synthetically, but in the real world, not quite, right? So, for example, let's say we have temporal data. We predict, let's say, the temperature for tomorrow. But yeah, today's temperature affects that. It's not completely independent, right? In temporal data, these errors are always going to be correlated. There's no way around it. If you look at genetic data, so let's say you want to figure out what are the causes or the driving factors of some nasty hereditary disease that is quite rare, let's say Hodgkin's disease. Well, not so many people have Hodgkin's disease. So if you now find or you get data with people with Hodgkin's disease, quite likely, because it's hereditary, that there's, well, let's say family lines in there. You have 5 or 10 people from this family, 5 or 10 people from that family. What could possibly go wrong? Well, the errors are not uncorrelated anymore, right? You start to overfit on individual families. Not every point was generated completely independently. So if they are correlated and you ignore this, you don't correct for this, you're not careful, then your method is going to say, trust me, look at my RMSE of 0.042, fantastic. And then you apply it in practice, and it's horrible. Because your assumptions were not met. So you need to be very careful there. Confidence intervals, I mean, they should be wider than, so basically all the machinery that I told you, it's going to break down, right? It's going to be overly optimistic. Just to illustrate this a little bit, right? Beyond time series, beyond genetic examples. Suppose that you just have your favorite data set and you want to, well, learn better coefficients. You could try to cheat. Why don't we duplicate your favorite data set? We don't have n data points, we have 2 n data points. Well, obviously we can now estimate much better our coefficients, except that we can't, right? Because of course we can duplicate, we can quadruplicate, we can push it to infinity. No, our coefficients are still as bad as they were when we only had 1 data set before duplication. However, if we now, after duplication, estimate a standard error, confidence interval, and so on and so forth, these intervals are going to be very small. Standard error is going to be very small. So you see the problem, right? But, in a way, what I said about the Hodgkin's, about the rare diseases, and the family traits, you could see this as a weird way of data duplication, right? I mean, everybody is unique. Well, some people are more unique than others, and within a family, you're least unique in a way. Errors are often positively correlated. And how can we possibly see this? Residual plots. There's clusters. If there's weird behavior going on, you have to be very wary. Yes? But the question is whether the correlation of error terms implies that the predictors are correlated. What do you think? You're not sure. That's why probably why you asked the question. Does anybody else have an idea? Does the correlation of error terms have a relationship, necessarily or coincidentally, to correlation between predictors? What? Definitely. Okay. Anybody else? Let's see if we have a contrary opinion. Yes, you? Interesting. Okay, interesting. So if you think that the predictors are correlated, it's necessary the error is going to be correlated. No, at least not in the understanding that I have right now standing here. So I might be ignoring a remote possibility, but no, my answer is no. Because correlation of errors is about individuals in the data set. That's what the correlation is about. Like in a family, within your family, your genetic makeup is going to be relatively similar to your parents, right? And well, much less similar to me, unless we are family without knowing it. That's what it's about. That doesn't say anything about the individual predictors. It's a different type of correlation. That correlation we see very, very soon. Yeah? Good. Okay. Another thing that we can pick up through residual plots, heteroscedasticity. Here, we again have a residual plot. And as you can see, it's not a banana, but something is clearly wrong, right? It is not a nice Gaussian band. What do we see here? We see that the noise, well, it is nicely zero-centered, so that is good, right? So we're not suffering from a massive bias problem, right? We're not have the wrong, it's not like a weird squiggly shape, there's no banana, but it gets wider and wider. The variance of the noise is not constant. And it's also one of the assumptions that we make. The variance of the noise is, it's always the same Gaussian. The residual, the irreducible error is generated by the same mechanism. Here it's clearly not. This means that, for example, that you have a machine that says bing, for example, right? And after you press a button, and if the machine is hot for whatever reason, well, it takes a bit longer to say bing than when it's cold. It doesn't always behave the same. Well, that is something that you need to take into account when you want to model things. Right? What temperature does the machine have? So how can you pick up heteroscedasticity? You see these funnels. You see over the input domain for different temperatures, would it be here, the fitted values, you see that all of a sudden it's much wider. One of my favorite examples, which actually we worked on quite recently in terms of causality, if you want to determine whether age and weight are causally related. Well, some people maybe believe that by losing weight they become younger, but yeah, it's actually more the other way around, right? But depending on which age group you are, age of weight kind of, no, age causes weight. If you're very young, you're not going to be enormous, right? If you're very old, then you can be enormous. There is a dependency there, and that is causal. That's also a form of heteroscedasticity. So between us, we're all adults, or at least I'd like to think so, right? Let's say 20 plus. There is a certain variance in our weights. Some of us are more slim, some of us weigh a little bit more, certain variance is all fine. Let's say this variance is this big. Okay, now let's project us back. We're now all 5 years old. What should this variance be? Is this the same? Yes or no? Yes, I see everybody doing like, yes. It would be a bit weird, right? To have like super slim 5 years, no, not a good picture, not a good picture. Heteroscedasticity. If you don't take this into account, things go wrong. How do you figure it out? Residual plots. Heteroscedasticity can also be caused by a lack of interaction term, because there is some interaction that then explains the variance. Okay. Now, problem 4. I have 6 in total, so we're almost there. Outliers. Outliers are points that, the definition I like best, are generated by a different mechanism than what generated most of the data. Right? They somehow come out of the blue, so to speak. They're strange, but not in a negative sense per se. Could also say are points whose outcome is far from prediction. This is a bit more introspective. I like this definition less, but it's in the book, so I'm not going to skip it. This point over here, yeah, pretty bad, right? Prediction. How can we pick up outliers, especially if we have a very high dimensional fit? Residual plots, because residual plots, we just flatten everything to two dimensions. For every point, we have a certain value. Outliers will get a very high residual, so we can pick them up. That raises the question, how large should the residual be before we say outlier? Right? Inliers and outliers. When is something normal or not? But what you can do is you can studentize the residuals. You divide by the standard deviation, or standard error, sorry. Then you get the plot here on the right, and you see that point 20 all of a sudden has a studentized residual of 6. Well, studentizing has again to do with fitting a certain distribution, very Gaussian-ish, and that means that if we get a value of 6, that means that we're in 6 standard deviations from the mean. We can compute what is the probability mass of being generated by that. That is going to be minute. So number 20 here is most likely indeed a residual, an outlier. Right? Typically, we say that if it's beyond the 3 sigma range, then it's an outlier. Okay, now, especially for the cybersecurity students in the room, if we have any. Do we have any left? Yeah, okay, okay, well, more than enough, more than enough. So outliers, just a fact of life, right? They just happen. What happens when outliers go bad? Or, let me change the question. Suppose that I could add now a data point to the data set. And I'm not benign, right? I mean, that's in this moment. I mean, I'm not dressed in black fully, right? Dark blue, but you can. What could I do? How could I, in a way, trick the model? Could I screw up the model? You are allowed to add one data point. Where would you put this? Yes. Okay, so I didn't hear, I think the third word, value. What type of value? Yes, yeah, exactly, yeah, we're there. Okay, yes, you? A negative value. Okay, well, that depends a little bit, right? So here, the input, well, -2, we already have quite some, so we could also, just like you said, then basically something like 1 million or something like that, right? That's what you said. You said -1 million. Both are equally bad / good. Yes? Why? Terrific. So to repeat, you said you had the right intuition, right? A very large point. You had the right intuition, a very negative point. But in the end, it depends on your data. If we have only very large values, then, well, you didn't screw up my model, you did. And the other way around. And you're always screwing up my model. Because you explicitly say, we're going to add a point somewhere where we don't have data. And that will affect the line massively because there's no other data points around it to compensate, right? That's what you said, right? So in a way, we can trick the model by adding what we call a high leverage point. Why does it have a high leverage? The further away it is from where we have other data points, the more it pulls the line down or pushes it up. So if we now have 0.20, right? So here, let's go back here. Adding 0.20 or not, there is some effect to the line, right? And so this is a benign outlier. Outlier is in the middle where we have lots of points, right? So there's a lot of density there. And if we now, up here in this example, 0.41 is, well, like basically you said, right? I mean, it's not 1 million, but it's high, right? But it's where we don't have any other data points. And all of a sudden, the slope of the line really starts to change. And this may not sound this dramatic, but this does mean that if we now ask for a value a bit extrapolated, let's say at -5, we're going to be very much off. If we now ask for a value at 5, +5, we're going to be very much off. I need a way to detect these things. And this is not really an outlier, right? Like in the previous sense, because it's actually, if you look at the residuals, the residual in the red line 41 is going to be relatively small. The studentized errors are going to be like, oh, this is insignificant. It's an absolutely benign point. Except that 20 was absolutely fine. I'm okay with having 20 in my data set, that the line moved a little bit fine. But 41, we should be very careful with. So, how do we detect those? If it's just a single dimension, it's easy. We just look at the tails. Where do we have very few points? There we need to be careful, right? So we need compact support. I already used this word 2 weeks ago. In high dimensions, it's much more difficult because we can't just plot it, and in high dimensions, all data becomes very sparse. So what we can do is we can fit, I'm almost done for those of you who need to catch a bus. We can fit essentially a distribution around it. In this case, essentially a Gaussian, and then we can see what is now the distance from that, right? So this point here is much more leveragey, much more problematic than this one here. This one is much more normal, right? So this one we want to be careful of, and not this one in this particular case. So that's what you can detect after fitting, you can look at the hat matrix, you can look at the Mahalanobis distance. There's different ways of doing it. But in the end, you want to find those with a high leverage score. Okay. Final. Collinearity. We already discussed this to a certain extent. You asked it just ago. You asked it a little bit earlier. What if we have predictors that are very similar, right? Well, they can substitute for each other. I can either choose the one or the other. And that may have trickle-down effects. So it's, again, an angle of attack. Right? So if I can somehow trick you into taking x3, and you don't take x4, and because you don't take x4, you don't take x5 and 6 and 7, you can steer the model in a completely wrong direction. These are very simple attacks on models, but they do exist. And even if you don't believe in that there is an adversary, because you're just looking at biological data and there's nobody who has any benefit in screwing you over, this may happen. You may have two genes that are very similar, and you choose either the one or the other, and yeah, before you know it, you forget or you don't see what is now really of interest. Credit data that we already saw, rating and limit are very related. So the rating is the credit rating, right? So how creditworthy is somebody, and the limit is the drawing limit. How much can they borrow? Well, yeah, obviously they're related, right? You get a high or a good rating. If you have a good rating, you get a high limit, and with that, so they go hand in hand. Age and limit are not collinear. They are basically independent. It could be that some people who are older, well, they make more money and hence have a higher limit, but they can't really substitute for each other that easily. If we look at this, we see this. So here we have a scatter plot between age and limit, and as you can see, something. So these are the people that make a lot of money, but overall quite uniform. Whereas rating and limit, straight on the line, very strong dependency. So how can we pick this up? One way to do it is to just look at the correlation between pairs of features. And if there's a strong correlation between a pair of features, bad news. Then we should choose either the one or the other, or always combine them both at the same time. Okay, they're like a joint deal, right? There's no escaping it. Why is it so important? Because here on the right-hand side, these are the effects of the coefficients from the one to the other. As you see in the top right, this has just been a nice, Gaussian from the top. There's essentially no effect. If I choose a high value for beta limit, then it has essentially no effect on beta age, just like it should be, right? On the other one, if I choose a high value for beta limit, then gives me a very low value for beta rating, and the other way around, because if I have the one, I don't need the other. Right? So this is what's going wrong. That's also what you see, that the one becomes insignificant or the other. Now, how can we determine this? I already said we can look at correlation. We can look at, and the correlation metrics then in general. This is a score, and I'm going to very quickly go over it because I don't like it so much anyway. The variation inflation factor. So in the end, what is now the variability of one of the coefficients, and how much does this get inflated or deflated by adding a collinear factor? So it's the variation of a certain coefficient. This we can just, and the VIF is the R squared. If we look at what is now the difference between the R squared of X, given the ones that we suspect, right, given the others, yes or no? If there is a big difference, okay, well then there's a lot of information. If it's very small, if we can essentially predict X very well given X1, X minus 1, collinearity. So it's a slightly different way of looking at correlation. It's now more predictability. Good. This I'm going to catch up next week. I apologize for being at least 2 minutes late. I hope you still enjoyed it. Thank you very much.